Section 4.5, Coordinates and Basis. A vector space V is said to be finite dimensional if there is a finite set of vectors in V that spans V, and is said to be infinite dimensional if no such set exists. So any set that's not finite dimensional is automatically infinite dimensional. It's only finite dimensional if we have a finite set of vectors to span it. If S is some set of vectors, as a set of n vectors, in a finite dimensional vector space V, then S is called a basis for V if S spans V, and if S is linearly independent. How about we show that the standard unit vectors form a basis for Rn called the standard basis vectors for Rn? So let's list our standard basis vectors, E1, which is 1, 0, 0, etc. Bunch of zeros. Then we've got E2, which is 0, 1, and the rest are zeros, and so on until our last standard basis vector, En, is just 0, 0, 0 until the last number is 1. Okay, so if we remember from example 1, 2 sections back, that was section 4.3, we checked that the standard unit vectors span Rn. Right? We can just multiply different linear combinations to get any vector in Rn. They take some constant times this one, plus some constant times this one, and so on. You can make any vector in Rn. Then we did a very similar example. It was also example 1, but it was in the previous section, section 4.4. And we showed that the standard unit vectors for Rn are linearly independent. So we really already checked the two conditions we need for our definition. So we could basically get this for free. These two things imply that we have a basis for Rn. How about we show that the set of polynomials 1x, x squared through xn is a basis for the vector space Pn of polynomials of degree n or less. So again, we'll have to check if the set spans Pn and if it's linearly independent. So how about we set P0 to equal 1, P1 to equal x, P2 to equal x squared, and so on, so that Pn is equal to xn. Okay, well, from example 3 of section 4.3, all the time we spent looking at spans, we see that this set spans Pn. And then from example 4 of section 4.4, we saw that the set was linearly independent. And therefore, this implies that this set is in fact a basis for Pn. In fact, we call this set the standard basis for Pn. Kind of like our standard basis for Rn, but for polynomials. As another example, how about we show that the vectors v1, v2, and v3 form a basis for R3? So we have to check that the set spans R3 and that the set is linearly independent. Okay, so how about we check the linear independence? Let's take C1 times V1 plus C2 times V2 plus C3 times V3 and set that equal to the 0 vector. We want to show that all of the C's have to be 0. So then this equation would mean that C1 plus 2C2 plus 3C3 is 0. It would also show that 2C1 plus 9C2 plus 3C3 is 0. All I'm doing is taking the linear combinations from the coefficients that are given in the components. So 1, 2, 3 gives my coefficients for the first equation, and then 2, 9, and 3 gives the coefficients for the second equation, and I'll get C1 plus 0C2 plus 4C3 equals 0 for the last one. Okay, so then this gives me a coefficient matrix of A equals 1, 2, 3, 2, 9, 3, 1, 0, 4. And the determinant of that matrix A is just 1 times 2, 3, 9, 3 plus 4 times 1, 2, 2, 9. All I did was cofactor expand along the last row. So I get 1 minus 0 plus 4 times the respective determinants. So that's minus 21 plus 20, which is minus 1. Okay, great. So the determinant is not 0. So therefore the C's have to be 0. So we have linear independence. Let's also check that this thing actually spans the set. So let's look at C1 times V1 plus C2 times V2 plus C3 times V3 equals some arbitrary vector B. We want to show that it could equal any B. So we get the same equations as last time pretty much. It's just equals B instead of equaling 0. So the components of B. So we get C1 plus 2C2 plus 3C3 is equal to B1. We get that 2C2 plus, or 2C1, sorry, plus 9C2 plus 3C3 is equal to B2. And we get that C1 plus 4C3 is equal to B3, where B1, B2, B3 is the vector B. Okay, notice this is the exact same coefficient matrix as for A, so that means same determinant. Determinant is not 0. That means that this thing has infinite solutions. So that means that the set of vectors not only is linear independent, but it spans R3 by the exact same reasoning, by just looking at the two equations and looking at the exact same coefficient matrix and taking a look at the determinant. Okay, so now we just basically more formally say that theorem 2.3.8 is what we use to make our inference regarding the determinant. That'll imply our spanning and our linear independence. So it implies our C1, C2, C3 being 0 in this case, and it implies B1, B2, B3 being anything in this case. So that implies that V1, V2, and V3 are linearly independent and span R3. In other words, they form a basis for R3. Let's do another example. How about we show that the matrices M1, M2, M3, and M4 form a basis for the vector space M22 of 2x2 matrices. So how about we start by writing out the equations we need. I'll do C1, M1 plus C2, M2 plus C3, M3 plus C4, M4 has to equal the 0 vector. I want to show that all the C's are 0. At the same time, I would like to show that if I looked at this equation but had an arbitrary vector B instead of the 0 vector, that I could actually get any vector b out of it by just, changing the coefficients around. So I can get both of these done probably the same time, just like last example. So I'll get C1 times the matrix 1, 0, 0, 0 for M1 plus C2 times 0, 1, 0, 0 plus C3 times 0, 0, 1, 0 plus C4 times 0, 0, 0, 1. And I want that to equal the 0 vector, which is the 0 matrix in this case. At the same time, I want C1 times 1, 0, 0, 0 plus C2 times 0, 1, 0, 0. And I should probably space those zeros out a little bit more. That's a little bit better. Plus C3 times 0, 0, 1, 0 plus C4 times 0, 0, 0, 1 for M4. Okay, that should equal an arbitrary B, so I'll denote that matrix as A, B, C, D, where A, B, C, D are any real numbers. Okay, so the first equation is the same thing as saying that C1, C2, C3, C4, right? Because I multiply C1 times this, I just get C1 on the left, I get C2 over here on the right, top, and so on. So I add up all of this, and then the left-hand side becomes C1, C2, C3, C4. The right-hand side stays 0, 0, 0, 0. But notice if the left-hand side is C1, C2, C3, C4, and it equals 0, 0, 0, 0, then that means that C1 has to equal 0, it means C2 has to equal 0, it means C3 has to equal 0, and it means C4 has to equal 0, by just equating the entries. Okay, so that gives us the linear independence. All right, linearly independent. And we'll do the same thing over here. We'll say that C1, C2, C3, C4, in this case, has to equal A, B, C, D, which means that C1 has to equal A, C2 has to equal B, C3 has to equal C, and C4 has to equal D. Okay, A, B, C, and D could have been anything, so that means C1, C2, C3, C4 can be anything. So this implies that this does in fact span M22. We do have infinite solutions here for our C's. Okay, so that means that M1, M2, M3, and M4 do in fact form a basis for the set of 2 by 2 matrices, the vector space of 2 by 2 matrices in this case. And in fact, if you were to look at M times N matrices, or Mn matrices, M by N matrices, with a single entry of 1, so basically M by N matrices, but with a 1 and the rest of the entries 0, just like these guys, then you could just extend this kind of basis to just an arbitrary Mn vector space, and you will get the standard basis for Mn. So this forms the standard basis for Mn by basically the same line of reasoning as we got this basis. Just a little bit more work and more writing. Let's now show that the vector space P infinity of all polynomials with real coefficients is infinite dimensional by showing that it has no finite spanning set. Okay, first, how about we suppose that it does have a finite spanning set? So how about we suppose that some set, say S, equal to, let's make up a bunch of polynomials. How about P1, P2, and since it's finite, we'll end at a polynomial PR instead of going on forever. And let's say that that spans P infinity. Okay, so that means that because we have a finite number of polynomials, there's some maximum degree. In other words, the degrees of the polynomials in this set S have a maximum. There's some polynomial over here with the biggest degree. And let's say that maximum is, how about n? So that's the degree of the biggest polynomial in S. Okay, so that means that any linear combination of polynomials that we make out of S will have to have degree at most n. Right? Can't get any higher than that just by adding and scalar multiplying them. Okay, so that means that we can't write the polynomial xn plus 1. It cannot be expressed as a linear combination of polynomials in S. Right? There's nothing that we could possibly add if we just are working with degree n polynomials to get a polynomial with a higher degree. But that's a contradiction. Because P infinity is supposed to have not only x to the n plus 1, it should have x to the n plus 2, it should have polynomials with degrees as arbitrarily big as you want. Okay, so we can't write xn plus 1 as a linear combination of polynomials in S, but we assumed that S spanned P infinity. So that means our assumption has to be false. S cannot span P infinity. Since S was an arbitrary finite set of vectors, that means there's no possible finite spanning set that'll span P infinity, which means that P infinity must be infinite dimensional. Notice it's kind of hard to think of a way to directly show that P infinity is infinite dimensional by trying to just like think about it being infinite, but it's much easier to think of it being infinite dimensional as in the sense of not being finite, or at least more easy to rigorously prove it. Which of the vector spaces in examples 1 through 5 are finite dimensional and which are infinite dimensional? Alright, well, we got some bases for Rn, Pn, and Mn. Right? They all had finite number of vectors in those bases, so that means that for examples 1 through 4, they were all finite dimensional. And then example 5, we just very clearly showed it wasn't. Example 5 was not spanned by finite many vectors. So that implied that it was infinite dimensional. In fact, we also have many other ones we have not discussed, like R infinity, kind of like Rn, but infinite. Well, I mean, Rn is infinite in a different sense. You have an infinite number of vectors, but you can imagine the vectors having an infinite number of coordinates. So we also have f minus infinity, infinity, our set of functions. We also have our set of continuous functions, c minus infinity, infinity. We also have our set of continuously differentiable, or functions with m continuous derivatives, or m derivatives, cm minus infinity, infinity, and the functions that have infinite derivatives, c infinity minus infinity, infinity. Next up, we have the uniqueness of basis representation theorem. If S is some finite set of vectors, it's a basis for a vector space V, then every vector V in V can be expressed in the form V equals C1V1 plus C2V2 and so on through CnVn in exactly one way. So there's only one linear combination that makes each V of those basis vectors. To prove this, consider S. Remember, it spans V because it's a basis. So that means it follows from the definition of a spanning set that every vector in V is expressible as a linear combination of vectors in S. To see that there's only one way to express a vector as a linear combination of vectors in S, let's suppose that some vector V can be written as this linear combination right over here, but it can also be written as another linear combination over here. So one has C's, the other has K's. Let's subtract the second equation from the first. So that means we have C1V1 minus K1V1. Factor out the V1, we get C1 minus K1 times V1, C2 minus K2 times V2, and so on. Since the right side of this equation is a linear combination of vectors in S, and we have S that linear independent, that means that C1 minus K1 has to be 0, because when we subtract these, V minus V gives us 0 on the left. So that means that each of these coefficients has to be 0 in order for us to have linear independence. So C1 minus K1 is 0, C2 minus K2, and so on. They're all 0. But we could just move the K to the other side by adding it. So that means C1 is K1, C2 is K2, Cn is Kn. In other words, these constants are the same. So that means that this linear combination is the same as this one. In other words, there's only really one linear combination. If S is equal to V1, V2 through Vn is a basis for a vector space V, and V is written as C1, V1, and so on, is the expression for a vector V in terms of the basis S, then the scalars C1, C2 through Cn are called the coordinates of V relative to the basis S. The vector C1, C2 through Cn and Rn constructed from these coordinates is called the coordinate vector of V relative to S. It is denoted by Vs, and it's just the vector you build out of those coefficients. All right, so how about we write the coordinate vector Vs, where V is Rn and S is the standard basis. In this case, we have V is equal to Vs. So, for example, in R3, we have, say, V equals some vector A, B, C. Remember, the standard basis is ijk for R3. So that means we would write V equals AI plus BJ plus CK. So that means that the coordinate vector is just the vector you take by pulling off of these coefficients. So it's just going to be ABC. So in the case of Rn and the standard basis, our coordinate vector is equal to our vector. That is not necessarily true, we're going to see. It's just cool in this case. I only did it for R3, but it holds for Rn. How about we find the coordinate vector for the polynomial p of x equals c0 plus c1x plus c2x squared and so on relative to the standard basis for the vector space Pn. Okay, in this case we have s is equal to 1x x squared through xn. So that means that if we take the coefficients, all of these guys, then all we get is c0, c1, c2 through cn. So in this case, the coordinate vector ps is not equal to p. It's just the coefficients that build p relative to the standard basis. How about we find the coordinate vector of this b, where b is a 2x2 matrix, relative to the standard basis for M22? Okay, so remember example 4. Let's write b equals a, b, c, d as a linear combination of the standard basis vectors for b. So that's a times 1, 0, 0, 0. It's just all those matrices that have a 1 and the rest zeros. So b times 0, 1, 0, 0 plus c times 0, 0, 1, 0 plus d times 0, 0, 0, 1. Okay, let's pull off those coefficients. Those are just the a, b, c, and d. Cool. So that means that relative to the standard basis, the coordinate vector bs is just a, b, c, d. We showed in example 3 that the vectors v1, v2, and v3 form a basis for R3. Let's find the coordinate vector of this arbitrary vector v, which in this case is going to be chosen as an example of 5 minus 1, 9. So we're just going to try to figure out what the coordinate vector of a more unique basis is, relative to a more unique basis for a random vector is. Okay, so let's write v as a linear combination of v1, v2, and v3. So c1 times v1 plus c2 times v2 plus c3 times v3. Okay, v is 5 minus 1, 9. We don't know what c1, c2, and c3 are, but we know what v1, v2, and v3 are. So let's plug those in and see if we can figure out what the linear combination should be. We'll just solve for the constants. We know that there have to be constants because this thing's a basis, as we've seen. So have to be some c1, c2, c3 that'll work. Let's solve some equations. We'll have c1 plus 2c2 plus 3c3 equals 5. We'll have 2c1 plus 9c2 plus 3c3 equals minus 1. And we'll have c1 plus 4c3 equals 9. Okay, how about we write out our augmented matrix? We'll do that as 1, 2, 3, 5, 2, 9, 3, minus 1, and 1, 0, 4, 9. Just by pulling off the coefficients. And we will reduce this. To start, how about I move the last row to the top, because there's a 1 and a 0 in the second position, so that'll make things a little bit easier for me. So I'll write 1, 0, 4, 9 up top, and then I will move this one to the second row, but I'll subtract the top from it so I can get a 0. So I'll get 0, 2, minus 1, minus 4, and for the bottom one I'll just subtract 2 times the top, and I'll get 0, 9, minus 5, minus 19, and that came from the second row. Okay, cool. I will then manipulate things further. I just need to divide this by 2 to get a 1 over there, and subtract 9 times that from the bottom to get a 0 on the bottom. So I'll keep the top the same for now. I'll get 1, 0, 4, 9, and then I'll get 0, 1, minus a half, minus 2, and on the bottom I'll get 0, 0, minus a half, minus 1. Okay, let's keep going. I'll divide this by minus a half, and I'll just add suitable multiples to cancel out the minus a half and the 4. So I'll get on the top 1, 0, 0, 1, and then I'll get 0, 1, 0, minus 1, and 0, 0, 1, 2. Okay, so that means that C1 is equal to 1, C2 is equal to minus 1, and C3 is equal to 2. So now I know what my constants are that make this linear combination true, which is exactly what it means to have a coordinate vector. So that means that Vs is equal to 1, minus 1, 2 in this case. Notice the coordinate vectors are not always obvious from your basis vectors and if you don't have a standard basis. How about we find the vector v in R3 whose coordinate vector relative to S is Vs equals minus 1, 3, 2. So in this case we have v1, v2, and v3 because we have the basis, but we don't know what v is. We don't know what the vector is. But we do know what the coordinates are, so that means we know what the constants are for the linear combination. So that's minus 1 times v1 plus 3 times v2 for the second coordinate plus 2 times v3. And then all we have to do is plug in v1, which is 1, 2, 1, plus 3 times 2, 9, 0, plus 2 times 3, 3, 4, and simplifying we get 11, 31, 7 as the vector